All right, this is Module 12, Lesson 3, which is Shoreline and Seafloor Features. So, the focus question today, why are all coasts not sandy beaches? So, maybe you've been down to Southern California and Northern California, and the beaches are dramatically different between the two. So, we're going to talk about what causes that. All right, so just a reminder, a breaker is where the wave collapses. So as the wave comes in, the wave eventually forms a curve and it breaks, so it falls down. And that's what people usually surf on, but that's called a breaker. All right, so here is the wave coming in. And so here's where the breakers are. So notice how the wave is starting to break and curl over. So that would be the breaker, and that's because the shore is getting shallower. So the energy, the wave is flowing in this circular pattern. And so when it gets and it touches the bottom of the shore, it starts to drag and it slows down on the bottom, but the top is still going fast. So it's a circular motion, so the wave, the top is going faster, so it breaks over. And then we can see some different areas here. We've got the shore. So the shore is where the waves come up onto the sand. And then we've got high tide versus low tide. So this is the area that the waves will cover during high or low tide. And then there's a variety of other things here. We've got currents, we've got the coast. So this is very typical of, especially Northern California, where we have kind of like these cliffs, and that's because of uplift from plate tectonics. All right, so beaches. Beaches are vast areas of sand, and the sand is deposited mainly by the ocean. And that's just from the wave action. So it's constantly physically breaking down the rock. And so it's making it smaller and smaller and smoother, creating the sand. All right, so when waves come in, the shoreline is not perfectly even. So the shore will have these what are called headlands. And so the waves are coming in, and once they come in, they are, if you think about the wave breaking, so the wave action occurring, so it's going to mimic the shoreline. So underneath the water generally mimics what's going on the shore. So as the wave comes in, here it's going to hit straight on. And then here it's starting to slow as well. So this is probably shallower than this because this is actually farther away right here, this distance, than it is right here. So the wave will start to slow down and curve around the headland. So as this headland sticks out, you'll see the wave kind of come in and curve around. And that causes erosion. So it causes a lot of erosion on the sides here. And so that's how we get big pillars and things that we see out on the ocean, um, especially in Northern California. All right, so it causes erosional features. It causes arches. It causes pillars. It causes the headland to erode further back, and it just creates a bunch of different varieties of features. And so some of these features are wave cut platforms. So you can see this is probably low tide, and then high tide. This isn't very deep, or it's very shallow. And so high tide probably comes in here. This is our shoreline. And so this is our beach. And so high tide versus low tide. So this is a wave cut platform. And this is too. So notice how right here, this is a wave cut platform. So it's basically eroding. If you can think of the hillside as going down like this. So in this picture, the shoreline would come down kind of to this point. So the waves are constantly eroding, and they're cutting back this cliff. And so we also get these features forming. So we get these pillars and things being formed, which we see a lot of in Northern California. And that's just by wave action. All right, so we get a variety of erosional features. The waves, like we said, are not hitting the shoreline equally. So they're kind of curving around. And so that causes these platforms to be formed. And so the waves are crashing around them. And these are just left over from the headland. So the whole headland, which is the mainland, used to come up and cover this whole entire area. And so, because the waves are hitting it at different speeds and different angles, it's created these stacks. So they're called sea stacks there. All right. So we have different types of currents. We have longshore currents are one of them. And so longshore currents run along the shore. So they run lengthwise along the shore. And so this is very common in California because we have the California current that comes down in our state. And so it creates these currents that run long ways. So we get these kind of troughs forming as the wave, as the currents go from up north down like this. And then, of course, you get wind blowing in towards the land. So you get these waves, but then you also get those deep currents as well. And so this can cause some issues with rip currents and things like that. So we do see that often here in California. And that creates these kind of ridges under the water, which can cause problems if you're not careful. All right. So those longshore currents, they move along the shore and they pull the sand downstream, so down the current. So the current is coming down. You can picture this as California. So the current is coming down here. This is the California current. And so as the waves come in, if you've ever sat at the ocean and watched, the waves will come in straight, or I mean, sorry, come in at an angle and then move out straight. And so they make this kind of zigzag pattern. So if you see this on the shore, the waves are coming in at this angle because there's a longshore current. But then when they go out, if you've ever watched the waves go out and it kind of like the sand is rushing by you, the wave is going always going straight out. And that's just due to gravity. But you can see the waves coming in at an angle and going out straight, in an angle, out straight. And so it creates this zigzag pattern which moves sand downstream. So the current is flowing downstream, and therefore the sand is flowing downstream as well. So I mentioned that longshore currents can create something called a rip current. So a rip current is a break in those troughs. So if we go back to this, you can think of these as troughs. And so let's say that there's a break in this. So it's not going to be even along the entire shore of California. And they change throughout the week. So we could have kind of a break where we have a current kind of pushing the sand away. And then, a couple days later, that sand could have filled in from that current. So rip currents occur and change all the time. So here's a real good indication of a rip current. We've got these breakers forming here. So the breakers are forming because the shore underneath is shallow. And so you've got breakers forming here, but notice how there's no breakers forming. So that means that this is deeper. And so what happens is the underwater current, when the wave comes in, it flows out under here very quickly because it's a straight path. It doesn't have to go over sand or anything like that. So it creates this really kind of strong current that if you're swimming there, before you know it, you could be way out here past the breakers. And that's how a lot of people drowned. Is because if you get caught in this current, you freak out, right? You're outside of the breakers and you want to get back to shore. So you're swimming towards the shore. Your natural instinct is to swim and go to shore. Well, what's happening is you're swimming against this really strong current and you're going to get tired. And when you get tired, you drown. So what happens if you ever find yourself in that situation? So let's say you're at the ocean and you find yourself all of a sudden way out here past the breakers. So the best thing to do is to swim parallel to the shore. So let's say you're out here, swim parallel to the shore, and then swim back. So when you see waves happening, try to swim in with the waves. If you try to swim against the current, you're going to lose. So just swim down a little ways and then back in.
As a fellow Michigander, and Ginger is also from Michigan, both of us got caught in rip currents in Lake Michigan. So fascinated by this next story you're about to do.
And as a child and growing up there, it happens all the time. So in the summer and spring, especially in the Great Lakes and also in the oceans, it's something that I've covered for years. But this time I went inside the rip current myself in the ocean, and here's what I learned.
It's one of the ocean's most deadly threats, more deadly than lightning, hurricanes, and tornadoes combined in an average year. That power forms as water piles up close to the shore. Then there's a break in the sandbar or bottom, and a fast-moving river rushes back out to sea. So my natural inclination, hit and one.
All right, so this is it. I am suiting up. It's funny because I haven't had a wetsuit on and I don't know how long. But let me grab this. I feel like the Avengers, superhero. Not quite.
So when you enter the water in front of us, you're going to take a diagonal path out. It should carry you northerly and diagonal out to sea.
Surrounded by safety, Patty, one of the San Diego guards, will be with me the whole time. And above, a Coast Guard chopper is monitoring everything.
I am definitely nervous, and mostly nervous because they tell me the water temperature is somewhere in the low 60s. Here we go. Oh my God. I just stepped out. I can feel it get deeper quickly, and the waves are not breaking where we are. That's a good sign that you're in a rip current.
Within seconds, I'm sucked out to sea.
And now I am really in a rip current.
I have been pulled hundreds of yards in less than a minute. Look how far I am from the beach.
What people end up doing is they're swimming and all they do is look straight out. When you turn around, all of a sudden, you're hundreds of yards from where you started. And that happened in seconds. So my instinct is to swim directly where I came from, but then I'm going to have to go against the current.
It's what most people do, and that's a mistake.
Swimming is very labored. It's definitely not easy. And I made absolutely no progress.
Then wave after wave, and panic sets in.
People look at where they started, and that's where they want to swim to. And when they can't get closer to where they started, they don't swim straight in. They panic, they get tired, and the more tired they get, the more they panic.
One arm up, and that's where the guards come in. They have me on the board and onto the beach in no time. Look at these rip currents from above. They can pop up anywhere along the beach, but what you need to know, they always form near piers and jetties.
We just got in within 2 minutes. We are hundreds of yards from the shore, and quickly we would be out in the open ocean. The current would carry us along the jetty all the way out.
And when I tried to swim straight back,
So just trying to fight the current a bit. No matter how hard I tried, I was not able to fight it or even make any progress at all. This is the strongest trip I've been in all day. The only reason I feel comfortable doing this is first show how powerful they are, but also because I've got a ride.
That's why you really have to respect it and know that it's a larger being than you are.
the point of me freezing and getting smacked in the face with these waves, though, to make sure you don't need help in the future. And a pleasant swim in the ocean would be just that.
Good morning, America! Taking on a lot of water there. Here's what you need to know to stay alive if you get caught in a rip current. This is very important as we go into this season. Number one, you have to stay relaxed. Next, this animation shows it. Rip currents are not that wide. So if you swim parallel to the beach, you will likely get away from that river of fast-moving water, and then you can get back to where you came from. You just don't have to go straight back. So there's all of these tips, but they said number one, if you have a lifeguarded beach versus a non-lifeguarded beach, you got to do that.
Great tips,
Great
great
tips,
piece.
Ginger.
Thank you,
Thank you.
Ginger.
As a fellow Michigander, and Ginger is also from Michigan.
All right. So the depositional features, if we look at the beach here, we've got these different headlands, we've got lagoons, we've got bays. So a lagoon, the difference between a bay and a lagoon is split off. So this is a bar that has split off this area from the ocean, whereas a bay is still open to the ocean. And then we've got a tombolo, which is just a piece of land that is basically the same. It's perpendicular to, or it's horizontal to the shore, and then this is perpendicular. So the spit sticks out, and this is basically just a longshore current is pulling out this sand here. And then same thing with this. We've got longshore currents that are pulling the sand along the shore, creating another spit here, creating some islands. Here's a lagoon here. So just a few little features there. But all of these things are formed on the coast. All right, so you can see these different features here. Here's a stream. So this is fresh water coming in. This is the bay. So we've got freshwater and saltwater mixing. That's where we have our estuary. And then we've got a headland, which is the area that sticks out. Then we've got these stacks that have formed because of erosion of this headland. And then we've got the spit that sticks out, but it doesn't quite connect. And then we've got cliffs. So we've got a variety of different features here. All right. I mentioned a few things about the spits and barrier islands. So a barrier island is basically just a bar of sand that runs along the shore. And it's because of longshore currents. It's separated from the mainland, so it's not connected. And so it's called an island because it's not connected. And because it's formed in this way, because the sand is pulling along the beach, it's causing it to be called a barrier island. So it's formed because of sand movement. And then a few other terms here that we talked about in the last picture. But the Baymouth Bar and Barrier Islands, they form areas, they kind of split off areas, and they're called lagoons. And then a tombolo is just a ridge of sand that forms between the mainland and the island that connects the mainland. So if we go back to that picture right here, you can see that is a spit in a barrier island that is connected. So it's called a tombolo, whereas these are not connected. And then this is splitting this bay. So it's blocking off the bay, creating that lagoon. All right, so we can see here are some barrier islands. So this is a barrier island here, and then this is a spit. So here's the bay, and then this is a spit, and you can see people have built on this. So this probably isn't the best place to build, and the reason is because this is in constant motion. So the longshore currents are constantly pulling sand, so this is constantly changing. And I wouldn't want to build a house on land that's constantly changing. That's probably not a good idea. All right. So if we look at the shoreline, natural causes that cause it to change would be storms. So we could have hurricanes. We could just have a natural big storm. We could have maybe a tsunami. So that's caused by an earthquake. Or human effects, building on the shoreline, changing the shoreline, taking vegetation off the shoreline. All of these things tend to change the shoreline, which is never really a good thing. All right, so if we look at these shorelines, and we're going to talk a little bit about climate change and oceans rising. So if we look at the coastal areas in the US, they only make up about 17% of the land area. Um, but they are home to over half the population in the US. So that's pretty significant. It's only 17% of the land, but 50% of the people, the population. So if we have 50% of the population living along the coasts and sea level rises because we've got melting glaciers, what's going to happen to that 50% of people? They're going to have to move, right? Or they're going to live underwater. So it's pretty significant. And so if they move inland, that is going to create a lot of environmental changes, including habitat loss because of building houses, and just a lot of negative things there. So not a good thing. All right. So in order to combat this, what we have built are things called seawalls. So a seawall reflects the waves. So the waves come in instead of eroding away the shore. A seawall is usually built out of cement. And so when the waves come in, they prevent that erosion because they're hitting cement instead of sand. So especially in areas that have a lot of tsunamis, they have built seawalls in order to combat that. All right, and then we have little things called groins and jetties. So these are things that people put in to prevent sand from moving downstream. So it's to help lessen the effects of longshore currents. So here we've got groins. So a jetty is a cement kind of thing to allow water to leave. So this would be like from a river or something like that, flowing into the ocean. And then these are groins, and so they're just outcroppings that it's kind of like an artificial headland. So it's areas where we've built usually rocks, like piles of rocks. In that video with the rip current, the last little part where she was swimming, there's rocks behind her. That was a jetty, and groin. And so it's just a natural, or not natural. It's a man-made structure out of rock that prevents sand from just moving down shore wherever it wants. So here we've got sand eroding, and that's because of the longshore current. But the sand is blocked from moving all the way down because of these groins. So the sand kind of stays in this area, and then periodically they can come and move the sand back. And so that way we don't have major erosional changes throughout the shore. We just have minor ones. All right, and then breakers. So breakers are kind of like artificial barriers or artificial bars, and they just break the current. So here you can see there are some breakwaters, and that helps to lessen the current that's in here. So let's say that there's a bunch of ships in here or something. So instead of having a lot of erosion occurring here, we've got these breakwaters. And so as you come around, this water always remains calm. So no matter how wavy this is or how turbulent this helps to break that wave so that the waves coming in here are not going to do some erosional damage. So those are called breakwaters when that is built. All right, so changes in sea levels. I mentioned that if we have melting during a warming period, like we have now, we have ice melting, glaciers melting. So that's going to cause sea levels to rise if we have a lot of melting water. During times of ice ages, we have lower sea levels, and that's because more of the water is locked up in ice. So as sea levels rise and fall, we can see shorelines being affected. And remember, we said 50% of people live along the shorelines. So that means that if we have global warming and glaciers melting, then we have some of the population being disturbed. So they're having to move elsewhere. So just know that in times of ice age, because water is locked in ice, then the sea levels will lower because there's more water locked in ice. And then when we have global warming, we have higher sea level because that water is melting and causing the sea to rise. All right, so the effects of sea level changes, a 70-meter rise. So think about 70 meters thick. So that's significant. That's huge. So if we had all of the polar ice caps melting, it would cause 70 meters. So that means that pretty much every single city that is near the coast would be underwater. So that's pretty significant when you have 50% of people living in those cities. But some of the features that have formed because of this are fjords, like you can see in the picture in the background. This is in Norway, and they're known for their fjords. These are glacier carved areas. So this was during the last ice age. This was glacier carved. So these are U-shaped valleys, and those U-shaped valleys are now flooded by ocean water. And so that is called a fjord, and they're very beautiful. But they are just formed by glaciers and rising sea level. All right, and then if we look at plate tectonics, which we'll talk about next semester, but areas like California are being pushed up because of the plates moving. And then we've got the oceans eroding. So basically, a lot of California, we see big high cliffs, especially in Northern California, because of uplift. And so that's why they're so high above the ocean, is because of that. And then we get lots of erosion occurring. So we have these headlands, we get slumps, sea stacks, we see sea caves, we see all kinds of cool formations because that uplift is occurring as erosion is occurring. And so it creates those cool features. All right, so getting on to what is under the ocean. So we've got a variety of things. We've got something called the continental margin. So the continental margin is this area of the continent. So this is still part of the continent, even though it's underwater. It's still part of that plate. And then here we have a different plate. And so this is part of the open ocean. And then you can see over here, we have another continental margin. So the continental margin is made up of the shelf, the slope, and the rise. So here is the shelf. So it's like a shelf. The slope is like a hill, like a slope. And then the rise right here is a very steep area coming up from the bottom. So the shelf, the slope, and the rise makes up the margin. Same thing with over here. We have the shelf, the slope, and then the rise down here. All right, and then along the shelf, we see a lot of canyons. So there's underwater canyons and rifts and ravines, just like there are above water. And that's due to erosion. So there's still gravity occurring underwater. So if things are eroding from the land and you've got currents happening, cold water is sinking and moving along, and that's creating a current. And remember the tank that we did, the current. So that current is pulling sediment along with it as well. So it's not just moving water, but it's moving sediment and all kinds of things. So we get features under there. So the ocean is just as vast and different as the above land. All right, and so those are called turbidity currents. So currents are created by density difference. And if we get currents, we get sand and stuff moving around. And turbidity refers to cloudiness in the water. So if we have excess stuff in the water, that's going to create more denser material, and that's going to create this current. And so it's called a turbidity current because it's produced by sediment in the water. All right, and then the last little bit was the rise. So that was the very end of that continental margin. So we had the shelf, the slope, and the rise. And this basically goes on to the abyssal plain. And the abyssal plain is fairly flat. The ocean bottom is not flat, but some parts, excuse me, some parts are. Sorry, it's really late. So some parts are flat, but not all of the ocean. There's trenches, there's ravines, there's all kinds of things. But the flat parts are called abyssal plains, kind of like where SpongeBob lives. All right, and so we get to the deep sea trenches. So the deep sea trenches are very deep. They go all the way down to the depths of the ocean. So some of the trenches, like the Mariana Trench, for example, is the deepest trench in the ocean. It goes down roughly about 7 miles into the ocean. So there's tremendous amount of pressure down there. It would crush you. So if you were to go down, the amount of pressure that's down there would literally crush you into a tiny human. So it's extremely strong. But that is the trenches where we have the deepest parts.
For the most part, we don't know what lies beneath the surface of our oceans. Most of the waters and ocean floor remain unexplored. But with new technology, projects are underway to find out what lies in the deep. Since 2004, a team of scientists has been cruising the Caribbean surrounding Puerto Rico, as well as St. Thomas and St. John Islands in the U.S. Virgin Islands, to create a comprehensive map of the seabed. NOAA, the National Oceanic and Atmospheric Administration, is the U.S. agency in charge of mapping, protecting, and managing some of these waters. They're updating old nautical charts.
So a nautical chart has soundings on it, discrete locations, but our map is continuous. We can see the ups and downs, the ridges, the ledges of the sea bottom. And all of that is important information for our manager, as well as to make the linkages between the seafloor habitat and the types of organisms that are using that.
The waters off the coast of St. Thomas and St. John have important habitat, including coral reefs. The waters have protected areas as well as areas where commercial fishing is allowed. Each year, the NOAA ship Nancy Foster zigzags through the water using sonar to scan the seabed. The ship emits more than 3,500 pings per second in a wide band, creating an image as if painting strips of data across the sea floor. Weeks of back and forth sailing in a pattern much like mowing a lawn yield traditional chart information, including bathymetry or depth in incredible detail. But the sonar data reveals a lot more than depth. Based on the intensity of the echo, scientists can tell if the bottom is hard, sandy, soft, covered in coral, seagrass, or other soft plants. By combining the sonar data with direct observations, NOAA creates detailed maps of the seafloor habitat. The ROV is a key to understanding the sonar data. Operated by scientists on the ship, it sends back video and still images. Then, the sonar data can be combined with the visual data. The researchers are looking for several answers to questions.
Why are fish going to a certain location? Are there behaviors that are going on? Are there certain types of fish that are going there? So those are kind of a very focused science application. And then there's other science that we conduct, which is applied towards a management community.
To effectively manage commercial fish species and protect non-commercial sea life, officials need to know the size of fish populations, where they are, and their overall health. The ship is equipped with what is basically a scientific-grade fish finder.
The technology that I'm using is very similar to commercial fish finders, or fish finders that your grandpa might have on his fishing boat on a lake, except these are scientific grade echo sounders. You can transmit a pulsive sound or a ping. That ping is transmitted through the water column, and it reflects off of anything that's in the water column that's of differing density than the surrounding media. That could be the bottom, which is very hard. It could be air bubbles that's produced by wakes, waves, or boats, or it could be gas bladders or swim bladders in the case of fish.
Each night, as the ship sails back and forth off land, Taylor's sonar spots the fish and adds important information to the maps.
The habitats are very important, clearly, but we need to better understand how fish are using those habitats so we can better understand how to manage the habitats for the fish.
After the sonar runs all night, attention turns to the ROV. Brian Costa uses sonar to pick locations for the ROV to explore.
It's just one of the tools in our toolbox to figure out. We can get a picture of what's down there in the image, but we don't necessarily know what is going on top of that 3D structure or what it's made out of. So that's where the camera comes in.
As researchers pilot the ROV deep under the sea, scientists note the health of the coral, types of fish, including the invasive lionfish, and inspect man-made debris, including lost fishing gear and even newly found shipwrecks. All of this data will help scientists better understand the reefs here and offer insights into ocean changes elsewhere.
One of the most important things about the work we're doing is we're characterizing coral reefs that have never been observed before. We're visiting new areas and getting that baseline of the health and condition and the extent of the coral reefs.
The NOAA scientists hope eventually to develop their techniques further so scientists can someday have maps of all the world's seabeds. For the most part,
All right, so mid-ocean ridges. So they're the ridges that run through the ocean, and they're where plates are separating. So mid-ocean ridges are where we have plates pulling apart, and we have a big one that runs through the Atlantic Ocean. And so it's just areas where we have, like I said, plates are pulling apart, and it creates fracture zones, and we have magma coming up and seeping up to fill it in. And so that's a mid-ocean ridge. And other features we see are seamounts and guyots. So these are underwater volcanoes, and so they have not made it to the surface. So a seamount is a volcano that is venting. So it's a volcano that may or may not become an island. And a guyot is an island that used to exist, but because it moved off of the magma source, it became extinct. And then water action, so the waves flowing over it, have eroded it to be level with the surface or just flat in general on top. And so those are called guyots. Coastal plain, and then we have our shelf, our slope, and our rise. And then we have our submarine canyons in there. We have our seamounts. We have our abyssal plain. And this shelf, the slope, and the rise all make up the continental margin. And then we have sea mounts and guyots, like I talked about. So a seamount is basically, a seamount is basically our volcano that is hasn't surfaced yet, whereas a guyot is an extinct volcano that has flattened. So this is kind of cool. So this is an area where it's a guyot, and it's flattened, and so it's formed an atoll. So an atoll is basically a ridge of area that's very shallow. So you can see this is extremely shallow, but it's an area where we have a lot of coral. So this is a volcano that used to be above ground, but it has weathered away to form a flatter area. And so when it becomes this kind of circular thing underwater, it's called an atoll. But if it becomes all the way underwater, then it's called a yield. And so when we look at the sediment on the bottom of the ocean floor, it is settled throughout the ocean floor and it's very fine grained. So it's this very fine, kind of like muddy kind of material. And it's basically just very fine silt, ash from on land, but just very fine sediment. And those are called marine sediments. And so here we can see some marine sediments, but then we see also some things called nodules. So nodules are minerals that are deposited, and this could be because of precipitation, meaning that it's hardened because the minerals came together underwater. It could be because it's at a hydrothermal vent. So hydrothermal venting causes minerals to form, and so those can form nodules, little clumps of minerals. And so that's what these things are. And so those can also be part of deep sea sediments. And then if they were part of something that was living, they're called biogenous sediment. So biogenous sediment is things that used to be living and things like maybe there's sea worms and cucumbers and all kinds of things that are living within it. So that's the biogenous sediment.
We're about to enter the abyss, the graveyard of the ocean, a ghostly landscape built of the skeletons of everything that sinks here. Hold your breath. We're on a journey to the bottom of the ocean. From the strange geology of the continental shelf, past the black smokers on the mid-ocean ridge, we're heading into the abyss. Almost 2.5 miles down, we pass the wreck of the Titanic. And then we're there. The seafloor between 2.5 and 3.8 miles down is known as the abyssal plain. The pressure here is phenomenal, enough to crush a soccer ball nearly to the size of a marble. This is home to the largest landscape on our planet. Put together, the abyssal plains make up more than 60% of the Earth's surface. This is the graveyard of the ocean. No sunlight penetrates this deep, but everything that sinks in the sea above comes to rest here. Ships, sea creatures, and snow. Drive along the seafloor of the abyss, and you drive through a blizzard, a snowstorm that has continued non-stop for thousands of years. This is marine snow, and it creates the flat seafloor of the abyssal plains. When tiny plants and animals living in the upper part of the ocean die, their skeletons start to sink. On their own, the cells of these plants are so small and light, they would typically take over 150 years to reach the sea floor. Many would dissolve before they got there. But scientists find that when glued together with the sticky mucus from small plants, called phytoplankton, they form large clumps that can sink in only a few weeks. This is marine snow. The flurry of marine snowflakes carries 815 million tons of carbon to the sea floor each year. For the animals that live here, it's like manna from heaven. They rely on it for food. Over thousands of years, marine snow and other sediment build up into a thick layer. When geologists drill through the sea floor in the abyssal plains, they have to drill through several hundred feet of sediment before they hit bedrock. They bring up core after core of gas-oozing mud, remains of marine snow, and other detritus. From top to bottom, the core of sediment from the deepest drill hole stretches for 3 miles. That's 11 times the height of the Empire State Building. Down here, wrecks of Spanish galleons and other sunken ships take thousands of years to disintegrate. But they're not the only things decaying on the seafloor.
All right, and we will learn about that later.
The graveyard of
Oops.
the ocean.
All right, so that is it, and I hope you enjoyed, and I'll see you next time.